Hello, boys and girls. I just got done watching a little bit of Mrs. Doubtfire, so I've got Robin Williams on my mind as I teach this lesson. I won't be quite as entertaining as he is, but hopefully just as informative. Okay, so this is section 6.2, and it occurred to me that maybe the easiest way to explain the theory in this section is just to go through the exercise at the end of the section, exercise 625. So let's go ahead and just do that together. And so for those of you who are taking the class, you can have a head start, a big head start on this problem, because I'm basically doing it with you. So here's what we're going to do. Let's go through it. Consider the dE y double prime minus y prime equals 0. So y double prime minus y prime, or y rather, equals 0. Do you agree that that is a second order linear differential equation? Second order because the highest degree of the derivative is 2, and linear because you're not doing anything special with the function or its derivatives. You can do whatever else you want with the variable, but nothing with the function. So that is linear. Okay, number one, what is the order? So let's just go through this. The order, as I just said, is 2. Secondly, write the dE in the form L of y is equal to 0. So here's the way you do it. L, in this case, is the linear operator d squared minus 9, because that's what you're doing. That's what you're doing with every function. So if you take L and you stick a y into L, what does L do to it? What does L do to this function? It takes the second derivative of the function. You can write it as d squared of y minus 9y, but d squared just means the second derivative. So it's y double prime minus 9y, and notice that this is being set equal to 0. So L of y is equal to 0. Okay, so that's number 2. And so what is L? There's L right there. Okay, show, number 3, show that L is a linear transformation. So how do we show that L is a linear transformation? Well, if you were to take L of let's take two different functions, y1 and y2. And what does L of y1 plus y2 say to do to it? It says to take the second derivative of that thing. So here I am. I'm going to take the second derivative of that thing and then subtract 9 of that thing. Okay, the second derivative minus 9 of that. And I know from calculus that if you take the second derivative of two functions, that's just the second derivative of the first function plus the second derivative of the second function. So the real guts of this comes from things you learn in calculus, where you learn that when you take the derivative of the sum of two functions, it's just the derivative of the first plus the derivative of the second. Similarly, this just comes from algebra. It's going to be 9 times y1 minus 9 times y2. And then I can regroup this and get y1 double prime minus 9y1. See that? Plus y2 double prime minus 9y2. And notice that this then is just equal to L of y1 plus L of y2. So that's the first thing that has to be shown in order to show that L is a linear transformation. That when you stick two different things into it, it's just L of the first one plus L of the second one. How would we do the second thing? We would start with L of some constant. Let me just call it alpha y. I'll just call it alpha y. is equal to, what's this? It's alpha y double prime minus 9 times alpha y. That's what L does to anything, right? What does L do to anything? It takes the second derivative of that thing minus 9 times that thing. But now, again, I know from calculus that if I have a constant in front of a function, that just stays there. I just take the second derivative of the function and I just multiply it by the constant. So this is just alpha times y double prime minus alpha times 9y. I can change the order of these two constants, 9 and alpha. And now notice that this is just alpha times y double prime minus 9y. And that's just alpha times L of y. Can you see all that? Yeah, I think that shows up. And so there's the other thing that had to be shown. A linear transformation has to have the property that when I put a constant times the vector, it's just if I take the linear transformation of a constant times the vector, it's just the constant times the linear transformation. I can do them in either order. So there we've shown number 3. We've shown that L is a linear transformation. Okay? Number 4. Is this linear differential equation homogeneous? Remember that to be homogeneous just means that it's set equal to a constant. If by the time you get done with the y's, you put everything with a y over here, and this is what's left over. If this were a what is my variable in this thing? It's a t. If this were a t, then it would not be homogeneous. I've got some variable there. But as long as that's just a 0, the answer is yes, it is homogeneous. The answer is yes. Okay. 5. How many elements are in the basis of the kernel? Okay, so let me remind you what's going on here. What do we know from our brief study of linear algebra? We know that the kernel of a linear transformation is a vector space. It's a vector space. We learned that in the last chapter. And since it's a vector space, we can talk about its basis. Its basis is what? It's a collection of vectors which are linearly independent and such that the span of those vectors gives you everything in the vector space. Okay, it gives you everything in there. We say it generates the vector space. Okay, and so once you have a basis, then you count the number of elements in a basis, and any basis is going to have the same number of elements, and that number is called the dimension of it. So that all helps us out with number 5 here. How many elements are in the basis of the kernel? And we're told this is where we use Theorem 6.2.1 from the previous page. Theorem 6.2.1 says the dimension of the kernel is equal to the degree of the differential equation. So since the degree or order, I sometimes use the word order, sometimes I use the word degree. I don't know why I do that. Right there, there's the degree. What is the order or the degree of the differential equation? It's 2. And so we know from Theorem 6.2.1 that the dimension is equal to the degree, which is equal to 2. So the answer is 2. Okay? So 2 elements in the basis. Okay, the dimension of the kernel of L is equal to 2. Okay, the dimension of the kernel is equal to 2, which means there's 2 elements in the basis. Okay, how about 6? By inspection, find 2 linearly independent solutions. Okay, so let's find two elements in the basis which are linearly independent. Okay, let's see if we can just find them from inspection. I think it's easiest if we write it like this. Y double prime is equal to 9y. Can you think of any function that by the time you take its second derivative, you just end up with 9 times the original function? That should first of all remind you of e, right? Because e to the t has the property that its derivative is equal to itself. If I had e to the 5t there, then by the time I take the first derivative, I'm going to get 5e to the 5t. What do we want? We want something that by the time we take the second derivative, we get 9. So can you see what we're going to need? If I let this y be equal to 3t, then watch what happens. Y prime is equal to 3e to the 3t. And y double prime, when you take the second derivative, you bring down 3 again, you're going to get 9 times e to the 3t. So sure enough, this is one thing that works. Okay, there's one solution to this, which is an element, will be an element in the basis of the kernel of this linear transformation right here. Okay, can we find another one? What about y equals e to the negative 3t? What happens when we take its derivative? Y prime is equal to negative 3 e to the negative 3t. And when I take the second derivative, the negative comes down again, and I end up with 9 again. See that? E to the negative, e to the 9 e to the negative 3t. So there are two solutions to the dE which are linearly independent. Why are they linearly independent? Because one is not a multiple of the other. If you only have two vectors, the only way they can be linearly dependent is if one of them is a multiple of the other. Otherwise, they are linearly independent. So you can't get one from the other. It's just like, again, if you're in R2, the only way in R2 that you can have two linearly dependent vectors is if basically one is just a multiple of the other. Then they're linearly dependent. Otherwise, if you have two vectors like this, they're linearly independent. Okay? So that's number 6. Okay? Explain why these, number 7, explain why these two solutions form a basis. Well, what do we know? We know that the dimension of the kernel is equal to 2, and so we know from Theorem 5 to 10, we know from Theorem 5 to 10, by Theorem 5 to 10, we know that two linearly independent vectors is going to be a basis, and then it's also going to span the whole kernel of this linear transformation. So by Theorem 5 to 10, these two vectors are a basis for the kernel of L. Okay, that's number 7. Okay, since they are a basis, they span all of the kernel. In other words, every solution of this form then can be written as a linear combination of these two things. Okay, since they're a basis for a kernel, that means that any solution, and I'm going to call, since we're talking about the homogeneous differential equation here, I'm going to write y sub y as the general solution to the homogeneous. Any solution is going to be just a linear combination of these two things. So I can just write it as alpha times e to the 3t plus beta times e to the negative 3t. So every solution to this differential equation is going to be of this form right there. It's just going to be some constant times the first one plus some constant times the second one. Okay? So that's number 8. Write a general solution, explain why it is a general solution. Okay? There it is right there. Okay, so that all uses Theorem 621 from this section. Okay? It just said basically just says that the dimension is equal to the degree of the differential equation. So since the degree is 2, all I need to do is to find 2 linearly independent solutions, and I've got my general answer right there. Okay? Now we're going to go on to explore Theorem 623. Okay, so here's how we do that. Look at number 9. Number 9 says, suppose that we have this differential equation. Y double prime minus 9y is equal to negative 18t. Okay? Notice that this is a non-homogeneous differential equation, right? It's second order, it's linear, but it's not homogeneous. It's non-homogeneous, okay? And so the question is, can we find a particular solution to this? So we're not looking for the general solution. We're just looking for anything that makes this true. And I tried to find something which you'd be able to look at and just guess at, okay? So just look at this. Can you read can you kind of see the puzzle? Can you solve the puzzle that I have in front of you? This 18 is a multiple of the negative 18 is a multiple of the negative 9. And I want something that when I take the second derivative, it just kind of goes away. So what if I just set y equal to 2t? Does that do it? If we let y equal to 2t, notice that by the time I take the second derivative, well, let's just do the whole thing. If this is my function, what am I going to get? Y double prime is going to be 0, agreed, because the first derivative is 2, the second derivative is 0. So it's going to be 0 minus 9 times 2t. And sure enough, I get negative 18t. So there's the answer. Y equals 2t is a particular, I'll just put y sub p there for a particular solution for that non-homogeneous differential equation. Okay? Now that I've done that one, see if you can do the next one. Y double prime minus 9y is equal to 45. Can you think of any function that satisfies that? Okay? Again, notice the nice relationship there. It wouldn't have had to be that nice, but I'm trying to kind of give a hint. What can y be so that when you do this, you get 45? What about this? What about just y equals 5? Does that do it? Notice that the second derivative is 0. I'm going to get negative 9 times 5. Oh, that's negative 45. That's not what I want. I want positive 45. So what if I make it negative 5? What if I make it negative 5? I made that mistake on purpose. I don't make all mistakes in life on purpose, but that one I did. Okay? If you make it just the constant. So this is y of t. It's just the constant. Y of t is just the constant negative 5. When I take the second derivative, I get 0. I take negative 9 times negative 5. Sure enough, I get 45. So yp is equal to negative 5. And now that I have several yp's, let's call this p1. Let's call this p2. Okay, there's the particular solution to that one. Okay, do I have room down here for the next one? Let's try it. So y double prime minus 9y is equal to negative 1 over t squared minus negative 1 over t squared minus 9 ln of t. Okay? Can you see that? That's, again, if you think about it a little bit, make sure that you're still with me here. Think about it a little bit. This function, this looks very much like this. So if you let y be equal to just the ln of t, then you're going to end up with 9 ln of t here. What happens when you take the second derivative of the ln of t? Let's just do it. If y of t is equal to the ln of t, then the first derivative is equal to 1 over t, and the second derivative is the derivative of that. That's, of course, t to the negative 1. So you're going to be negative t to the negative 2, which is negative 1 over t squared. Ah, that's exactly what we had. See that? So there's our particular solution right there. Okay, so there's that. Okay, next one. Find general solutions to each of these things. Okay, so we found particular solutions. What would the general solution look like? And so the general solution, look at what the theorem says. This is the guts of Theorem 623. The general theorem, this is what's cool about linear differential equations. All you have to do is take the solution to the homogeneous one and add the particular. So let's use y sub g for general, and I'll put 1 there again. It's a general solution for this differential equation. It's going to be what? It's going to be alpha e to the 3t plus beta e to the negative 3t, and then you throw on, your solution, your particular solution, plus 2t. There it is. So there is the general solution to this. Every solution to this differential equation is of this form. Okay? So that's what's cool. All we have to do is to find the solution to the homogeneous, and then we throw on the solution to the non-homogeneous, this particular solution, and you combine them together, and you've got the general solution of this. Okay? So you should be able to figure these out. I'll let yg2 is going to be what? Alpha e to the 3t plus beta e to the negative 3t, what? Minus 5. And you can finish that one up. Okay? So that is number 9. Okay? Or number 10 rather. Okay? Number 11. What is a particular solution? This is number 10. Find a particular solution to this. Y double prime minus 9y is equal to, is equal to negative 18t plus 45. What? And then all this stuff. Minus, I'm going to have to go down in one row, minus 1 over t squared minus, let's see, is that a minus? Let's see, yeah, minus 1 over t squared minus 9 ln of t, minus 9 ln of t. Okay? What is a particular solution to this? Let's just use y of p for this thing. What's a particular solution? This is where, look back on the previous page, Theorem 624 is really helpful. It says if you have a couple basically, if you have the particular solution to this thing, and you have the particular solution to this thing, and you have the particular solution to this thing, then the particular solution to this is just what you get by adding these 3 particular solutions. So it's just going to be what? It's just going to be 2t, minus 5, and then what? Plus ln of t. And the whole reason why this works so nicely is, again, because this thing is linear. Everything can just be broken up. Nothing. Remember the difference between taking the derivative of the sum of two things versus the product of two things? When you have the derivative of the sum, all you do is just do each one individually, right? You just take each one individually. Okay? That's really easy and convenient. As soon as you put a multiplication there, then things became more difficult. You had to remember the product rule, and you had to take the derivative the first time, all that kind of stuff. So the point is, a linear DE is one that has this really nice property that all the sums and products by constants, everything just works out very nice. It just kind of, you can break it up into its pieces, and you can just do each one individually. So this thing here, if you wanted to, you could go ahead and try it out. Go ahead and try this out if you want to. Stick this thing into this DE, and you'll see that you're going to get this for an answer, because each of these pieces just gives you those three things. They can all break apart, and you can get each one. So that's number 10. And then number 11 is kind of hopefully what you expect by now. Now that we have the particular solution to this, what's the general solution? The general solution is just going to be the homogeneous solution plus the particular. And here's the particular. Okay, so there you go. So this problem, I intended to basically help you understand the theorems of this section, which are going to be used through the rest of the book, the rest of these sections. And I intended this to be an exercise that you do, but as I thought about it, I thought, oh, this is maybe a better thing to do as an example. We'll go through it carefully together, and then you'll be able to apply this as we do other problems in the future. So this is still to be handed in if you're taking the course, but there I've helped you out with the whole thing. Okay, very good. So that was section 6.2 right there.